Okay, so what we're going to do is take chapter 10 Lewis structures and add to it geometry. So we didn't do this part in intro. So we're adding to obviously what we covered in intro Lewis structures. We added to that like the formal charges that we saw in the last chapter and then expanded octet. And what we're going to look at now is the actual geometry of the structure and then the orbital hybridization. So what we mean by that part is we learned about S and P orbitals. We kind of talked about how, in covalent bonding, electrons are shared, so the orbitals overlap. But if you ever kind of sat there and thought, well, how does a p orbital overlap with an s orbital? Like if you think about a bond between carbon and hydrogen, you're thinking about carbon having empty spots in its 2p orbitals, but hydrogen having an empty spot in its 1s orbital. So how does that happen? So what we're going to look at is when bonding occurs, the s and p orbitals don't actually stay s and p orbitals anymore. They hybridize, they morph into the geometry that allows that orbital overlap. And that's the geometry we're going to see when we look at the Lewis structures. So the two are actually tied together really nicely. So on the first page of the chapter 11 notes, we're just going to kind of go through the main electron geometries. And I've got those listed on this piece of paper just to get us started. I had printed out the notes and then I left it at home. So it was sort of a mad rush this morning to get out the door. Sorry, felt like I was just kind of behind, like those days when you wake up and you're already behind. That was today. So I'm going to just kind of be going back and forth looking at, but I'm going to come from the notes so you can follow with me if you've got the notes printed out. So these are the main electron geometries. So there's going to be molecular geometries, which are more specific, but these are like the main groups. And basically what we're looking at is in this notation, A just refers to any center element. And then X are the bonding elements that are bonded to the center element. And 2 or 3, 4, 5, or 6. The first one I think is intuitive. What we're looking, let me kind of start out by saying that what we're looking to do is always maximize the bond angle or the distance between either lone pairs of electrons or bonding pairs of electrons. And we only look at the geometry for the center element. So just as an example, if we had carbon dioxide, so we remember seeing this back in the previous chapter, it has 2 double bonds of the oxygen to the carbon center. When we look at the geometry, we're just looking at the carbon and the bonding pairs that are on the carbon. We're not looking at the oxygens. It's only the center element. So that would be my A, the carbon, and then X2. There are 2 bonding elements here. And it turns out that when we do AX2 notation or AX3, whatever it is, it doesn't matter if the bonds are single, double, triple. That part doesn't matter. It's just A is your center element. X2 is how many bonding elements there are on the center. So AX2. And this turns out to be a linear structure. So in lab this week, what we're going to do is we're going to take the ball and stick models, which are kind of fun, and carbon. Every kit's a little bit different, but this carbon is the black. But I won't necessarily stick to that. I've already got some that are already set up, kind of ready to go. So I won't stick to black always being carbon. And red is going to be our oxygen. And so what we have here is a double bond. And then when you get into organic chem, you start to look how that obviously reduces rotation on that bond. When it's a double bond, it no longer is free to rotate. So it just kind of changes some of the chemistry of it, but that comes later. But when I look at my carbon and 2 oxygens, they are in a straight line. And so what we look at, and I know these kind of flexible bonds are kind of strange to look at, but what we're imagining is that we have these bonding pairs of electrons, and on the other side of the carbon, another bonding pair of electrons. And we're trying to maximize the distance between those bonding pairs of electrons because electrons repel each other. So linear is pretty good. It's 180 degrees. We can't really do much better than that. So carbon dioxide, nice linear molecule. So just for the geometry right now, just to get that notation underway, AX2, all right, and that's a linear structure. All right, then when we look at AX3, this one is trigonal planar, and planar obviously means that we're going to be in a plane. Boron really loves trigonal planar, and the reason for that is boron is a common exception to the octet rule. It typically only does 3 single bonds. If we imagine boron right above aluminum on the periodic table, it has 3 valence electrons. And rather than trying to fill the octet, it typically will just do 3 bonds. And what we do here is we have a max bond angle of 120 degrees. And obviously each of them are going to be that same 120-degree bond angle. And so if I looked at, I don't know, let's just say this was boron trifluoride. Sorry for kind of squeezing that in. So BF3. What you look at here is you would have your boron in the center, and then you'd have your 3 fluorines attached, and 120 degrees times 3 is 360, right? So there's your complete circle. So pretty nice large bond angle, maximizing the space. Again, the bonding pair of electrons and the bonding pair of electrons that want to repel. So that would be trigonal planar. Planar because obviously it's in a plane, right? So it's kind of appears two-dimensional that way, right? It's not going up or down. It's just in a flat plane. And trigonal, right? Because it makes a triangle. So trigonal planar. Now, tetrahedral, this is carbon. For the most part, carbon typically likes to be tetrahedral. And like I said, I didn't stick to the black being carbon, but carbon is going to be your most, well, a lot of things do tetrahedral, but this is when there are 4 bonding elements. Carbon, like we know, has 4 valence electrons. It really likes to take 4 bonds. So methane, natural gas, right? So CH4, don't worry about the dashes and that's just my pretty poor way of trying to draw this 3-dimensionally. I remember learning this in organic, you know, like the kind of bolded line and the dashed line, but don't worry about that. I am not a good 3-dimensional drawer. I don't even really draw good stick figures, frankly. So, but tetrahedral, the balls and sticks always kind of help me see that. So at first glance, looking down with the camera, this may look like those 3 attachments here. They kind of look almost like the trigonal planar, like we saw with the BF3. But what's happening in this case now is if I rotate it, because of the bonding pair of electrons sitting up top here, also pushing against those 3 bonding pairs of those down here, right? Instead of them staying in a plane like we saw here, they're actually, you can see that side to side, like this is the boron trifluoride, the trigonal planar that we just looked at. This is on the left, the tetrahedral, and those 3 bonding pairs, right? They're making like a pyramid base. So it's pushing those down. And the reason for that is if we had kept this in a straight flat plane and you had your bonding pair up here, that means that from this, let's say there was one going straight out to the side and then the one going up, that distance, right, between those 2 bonding pairs of electrons would only be 90 degrees. And we can do better than that, again, trying to maximize the space. So the bonding pair of electrons on top here pushes those 3 that almost look like they should have been trigonal planar. It pushes them down into like a tripod position. And now all of the bond angles here maxed out 109 roughly degrees. Now, I don't worry about memorizing all the bond angles because why would we? But again, what we're looking at here in terms of the notation is you have your center carbon, 4 bonding elements. So that's why you have an AX4 tetrahedral shape. So that's your tetrahedral shape. All right. And so if I'm trying to draw that, again, my drawing skills, not so good. So these 2 right here, these 2 hydrogens are in a plane, right? And then one's going down and back and the other one's coming out of the page. So there's your CH4. Then trigonal bipyramidal. What we have here is a center element with 5 bonds. And so this is obviously going to be an expanded octet because we now have 5 bonds around the center element, right? So that means you've got 10 electrons or 5 bonding pairs. So we've gone past the octet, and what we talked about in the last chapter is that's only possible when you have a row 3 element or below on the periodic table. So row 3, 4, 5, 6. And that's because these elements, remember in energy level 3, we do have 3D orbitals. On the periodic table, it doesn't show up until row 4, but they are 3D. So we're going to see that when we talk about the orbital hybridization, that phosphorus, for example, it can hybridize its s and p orbitals, but also d orbitals, the 3D orbitals. And when that happens, right, we have expanded the octet. So trigonal bipyramidal. So almost what you look at here is this starts out looking like that trigonal planar. If I took these 2 off for the boron trifluoride. So these are all 120 degree bond angles. And then if I flip it on its side, you can see that I've got another bond going up and another bond going down. And so bipyramidal, two pyramids, and trigonal shape. So you almost think of this like a trigonal base, and here's a pyramid pulling up. And then if you flip it, there's another pyramid shape going in the opposite direction. So it's like there's a pyramid and then a pyramid, like stacked on top of each other. And this is the triangular base. All right, so trigonal bipyramidal for AX5. And I won't try to, well, no, I don't know. I'll try to draw it. Why not? So let's do phosphorus pentachloride. So phosphorus, chloride, and then I can say there's my chloride. And then one would be out and back and the other one's forwards or something like that. Again, I always got the dashes and the bolded line backwards anyway. So one's going back into the page, one's coming out in front. That's like, it's like the limitations of my brain. Drawing is one of them. Okay, so that's AX5. And then AX6, again, another example of where you're definitely going to have an expanded octet. And this one I remember as a student, I was like, why octahedral? Didn't we all establish that octa means 8? But anyway, and I always thought, well, why didn't they call this square bipyramidal? Because we'll see square pyramidal later. But now what you have is a square base, and it looks like a pyramid shape, right? And then another one on the bottom. So I always thought this one should have been called square bipyramidal, but they didn't ask me. So it's called octahedral. So in this plane, in this center plane, right, you've got 90-degree bond angles, right, between each of those bonding pairs. And then the two up and below make, kind of, there's a 180-degree right there. So that's a linear shape right there. And then you've got this kind of nice square here. So that's octahedral. Sulfur is a big one for octahedral. So SF6. Some of the noble gases will do that when they bond. So again, trying to draw this. So S and then F, right? That's the straight line that we were kind of looking at up and down. And then if you think about this, you're going to have, I think, one going in the back. I'll draw this way. One coming out in the front. One coming out in the front, and then one going out in the back. All right, so there's your octahedral shape. So those are your main electron groups. So what we have here is we don't have any lone pairs on any of the center elements. These are just our main electron groups. So kind of going back out again. AX2, AX3, AX4, AX5, AX6. We don't have any AX7 or anything past that. That's it. But what we're looking at is a center element and then how many bonded elements there are. And on each of these examples, there are no lone pairs on the center element, okay? Because that'll change the geometry just a little bit. So first page of notes, that's what we looked at. We looked at carbon dioxide. Now, the next example on the first page, it says, let's look at the geometry of silicon tetrachloride. All right, so if I look at SiCl4, what I'm looking at here is we can imagine, I think it's probably going to look a lot like CH4. And the reason why I say that is carbon and silicon are in the same family. So we have our silicon center element. And what we know is it comes in with the 4 valence electrons. And then the chlorine, right, comes in with 7. So it would want to take 1 bond to finish out the octet. And so what I was going to do here is if we kind of drew this in the last chapter, we would draw it just sort of in a straight plane, right? Or in a plane, right? We wouldn't be worried about 3-dimensional geometry here. We would just kind of be looking at it as, okay, here's our silicon center. We've got 4 bonded chlorines. But now that we're sort of understanding that this bonding pair of electrons repels against this bonding pair against this one, right? They all repel against each other. Instead of just having a planar molecule with a 90-degree bond angle for each of these, this is where we get that tetrahedral shape. So this bonding pair is going to push those 3 down into sort of a pyramid shape. And so again, if we're going to draw this in an updated way, right, for chapter 11, we still have our silicon center. We still have our chlorine and our chlorine. Those could be in the plane. So if I'm sort of looking at this, right, this would be in the plane of the paper. And then I'd have one coming out and one coming back. All right, so one coming back, one coming out, and there would be my tetrahedral shape. All right, now, Also, when you start doing these Lewis structures kind of a lot with repetition, like we do in this chapter and the last chapter, you probably would rather not have to go through the motions of counting all the valence electrons, checking to see, right? And so you do kind of get faster and faster with these. You kind of know coming in, silicon group 4 wants 4 bonds. Chlorine, a halogen typically only wants 1 bond, especially if it's terminal, it's only going to do 1 because it's the more electronegative. Formal charge wants to be 0, so it's going to take 1 bond most of the time. So you can almost sort of look at this and say, okay, this is going to make sense. Silicon's going to bring in 4. Each of the chlorines are going to bring in 1 for that bonding pair. The octet for everybody will be satisfied. This looks like AX4. All right, and then you'll know tetrahedral. The next one we had was the antimony. Sorry, I think it was pentachloride. Let me just double check on my notes real quick. Yeah, antimony pentachloride. And so for this one, antimony is group 5, and just like arsenic or phosphorus. And then we would have 5 bonding chlorines, and that's going to be this shape here that we looked at, the trigonal bipyramidal. So we'd have the chlorine, the up and down chlorine in a plane, right? And then this one also in that plane. So this is sort of my plane right here. And then I'd have 1 going back and then 1 coming out into the front. And that would be my AX5. And then again, that one was called trigonal bipyramidal. All right, and bipyramid, right, 2 pyramids, and trigonal because it's a triangle base. And again, pyramid because there's a pointy point going up, right, and then a point going down. So there's like a pyramid base and a pyramid top. All right, so that's the AX5 trigonal bipyramidal. So in the notes, we look at those 2 geometries, and then on the next page, I ask you about a specific compound, and it's sulfur tetrafluoride. And I ask you why that's not tetrahedral, right? So for this one, oh, it froze. Sorry, just 1 second. Let me stop it and start it back over again. So sulfur tetrafluoride, not tetrahedral. The reason for this is when we were looking at the silicon tetrachloride, and that one was tetrahedral, we know that silicon is group 4, 4 valence electrons, takes 4 bonds. Each of the chlorines will supply a single bond to the silicon, and then everybody gets to complete the octet. What's different here, though, is that the sulfur is group 6, not group 4. So sulfur actually comes in with 6 valence electrons, which means it's going to take 4 bonds with the fluorines, but then it's going to have an extra lone pair sitting there. And so what happens now in the notation is that you still have the AX4, there's 4 bonding elements, but now the lone pair here means that we have an E. E is for the lone pair of electrons, and E is for each pair, right? Because we don't deal with free radicals here, so it's not like you'd have a single electron anyway, but each lone pair represents an E. So this would be an E1 because there's 1 lone pair on the sulfur. And that lone pair also repels just like the bonding pairs did. So it won't stay in this tetrahedral shape because now there's going to be another lone pair of electrons that wants to sort of span out, right, and maximize that distance. So what you look at here is you have 4 bonding pairs around the center element plus another lone pair. So you have a total of 5 groups around the center element. 4 of them are bonding groups. 1 of them are lone groups of electrons, pairs technically, but we still come under the sort of the main umbrella of an AX5. So if I go back to my AX5, that was this one, the trigonal bipyramidal, right, where we have 2 max out linear 180 degrees, and then these 3 are in the plane. So AX4E, it's not going to stay tetrahedral because we now have 5 groups of electrons around the center element rather than just the 4 that we had over here with tetrahedral. All right, so I know playing with these in lab is going to probably be helpful. So it starts out sort of with that same basic AX5 main electron group, but then it has a more specific molecular geometry. That's the big thing. So in the notes, and I'm going to kind of go over to my share screen here for just a second. When you share, or not when you share, can't do two things at once. When you look at the notes, what you're going to see is I've got this chart, and it'll basically show you in bold, right? You have your AX2, like we talked about, being linear, AX3 trigonal planar, AX4 tetrahedral, and we're looking at the AX5 main electron group, right, which is this trigonal bipyramidal. But when you replace one of those bonding elements with a lone pair, which is what we're looking at for this sulfur tetrafluoride, you end up with a shape that's called seesaw. All right, so if I go back to my other part here, and whoops, okay, so cooperate. Oh, okay, nope, don't do that. Okay, there we go, sorry. All right, there we go. So when I come back to here, what I look at is I'm going to take one of these, assuming that this was a bonding element, sort of that AX5 main geometry we had, the trigonal bipyramidal, and I'm going to take one of those off. And so now what we have is this is a lone pair of electrons, right? Just sort of sitting there. So that's representing this lone pair on the sulfur. And then we still have the 4 bonding fluorines. And so what we look at here, this shape is called seesaw, because that's exactly what it looks like. So when you play with this in lab, you'll see you've got sort of that seesaw shape, right? So you've got like a base, and then this can teeter just like a seesaw. All right, so that is a seesaw geometry. So not tetrahedral. So the question was, you've got 2 compounds that look pretty similar. You got SiCl4 and SF4. And we saw that the silicon tetrachloride was tetrahedral. And the question was, why is SF4 also not also tetrahedral? And the reason is that lone pair, right? The silicon tetrachloride didn't have that. So it was able to maintain that tetrahedral shape. But with the SF4, right, now we've got this lone pair on top repelling against those 4 bonding pairs, and that creates that seesaw shape rather than tetrahedral. So always the idea is maximizing the bond angles between either the bonding pairs or the lone pairs of electrons to try to maximize the distance between those, because of course they repel. All right, so if I go back up to the notes, we've got chlorine trifluoride. And the question here is, why is this not trigonal planar? All right, and when we looked at boron trifluoride, it was trigonal planar. And I think you probably can see where I'm going here. The reason is that the chlorine is going to have extra lone pairs of electrons. So chlorine bonded to a fluorine, bonded to a fluorine, bonded to a fluorine. You might look at that and be like, yeah, that should be trigonal planar, right? Just like what we saw with the boron trifluoride. Each of those bond angles can be 120 degrees, nice plane, triangular. But chlorine ends up here with 2 lone pairs of electrons. And so we think about it, chlorine comes in with 7 valence electrons, right? So 1, 2, 3, 4, 5, 6, 7. Each of the fluorines come in with 7. So formal charges here all would be 0. Chlorine has an expanded octet. And in that sort of notation, we would have AX3, right? Because there are 3 bonding elements. That's just like the boron trifluoride. But now when I look at it, I have an E2, right? There's 2 lone pairs on the chlorine. So when I look at this, the 3 plus 2 means I'm in a total of 5. So I'm still under that AX5 umbrella. So if I go back to that chart, the AX5 umbrella would be the trigonal bipyramidal. But what we're looking at is now, instead of the seesaw like we saw for the sulfur tetrafluoride, now we've got the 2 lone pairs, the E2. And so now this structure is called T-shaped. So I can go back and show you what the same structure. So we're looking at kind of that same AX5 basic shape, but now there's only 3 bonding elements left, right? And so I'm going to take one of these off. There we go. And you can see it looks like a T, right? So now this is T-shaped. So it has the same AX5 start or base. But again, there's the lone pair here and there's another lone pair here. So that means it's not going to be that 120-degree bond angle like we saw with boron trifluoride, because these are in the way. Those lone pairs are in the way. So this one would be T-shaped. All right, so T-shaped just because it comes under that AX5 umbrella. All right, then again, the AX5, the notation, that's the main electron geometry. The T-shaped here, that's called the molecular geometry. All right, so molecular geometry versus electron geometry. So the AX5 trigonal bipyramidal, that's like the main group, I call it the main umbrella, right? And then within that, more specific is the molecular geometry, which is T-shaped. All right, so that's what we're going to be practicing this week in lab, is just playing with the balls and sticks and then kind of seeing where everything goes. All right, so next thing we got to talk about is whether or not a molecule will be polar. And there's a couple of compounds that we want to look at in the notes. We've got HF, we've got CF4, and then we have CHF3. All right, so polarity, this is going to be a little bit different because what we've talked about with polar and nonpolar so far is just with regard to a bond. So we're going to review that first with the HF. So what we talked about was when you have a covalent bond, right, the electrons are shared. And we remember drawing the circles, you know, right? And we talked about, okay, there's the shared bonding pair of electrons. Are they shared evenly? And what we remember is fluorine is our most electronegative element. So the analogy my brain made with this was tug of war. Fluorine is pulling really hard for that bonding pair of electrons because it's so electronegative. Hydrogen is electronegative, but about half as much, right? So it's not going to be able to pull nearly as hard in its direction. And so overall, you're going to have an uneven distribution of that electron pair. It's not going to be evenly distributed between the two. It's going to be much closer to the fluorine side. It's going to be distorted. And what we said was, you know, electrons are negative, so it creates a negative end and a positive end, but it's not a full +1 -1 because that would be an ionic bond. So we use the little curvy D dipole symbol. So this would be my negative side, my more electronegative side. The hydrogen would be my electron poor or partially positive side. And that creates polarity, right? So it's polar because it's like poles on a magnet. There's a positive end and a negative end. So what happens when we start looking at the overall molecule is now we have to take into account some physics. At least that's kind of what it reminded me of. Now, HF is just a binary molecule. So the bond and the molecule, it's the same answer. It's polar. But when you have more than just one bond in the molecule, now you have to really think about all of the equivalent forces that are going on here. But there's a simple way to think about it. The CF4, like the CH4, this is going to be a tetrahedral shape. And so what we would have is our sort of triangular pyramid base, right? That little sort of tripod. And then the fluorine sticking up. So that was this shape here. And we know that the carbon fluorine bond, if I didn't have any other fluorines here to worry about, if I was just looking at the carbon fluorine bond, it would be polar. Because again, fluorine, much more electronegative than carbon, just like it was with the hydrogen. So we would be pulling most of that electron density for that bond up towards the fluorine. But what's happening here is we're also pulling down and out and down and out and down and out. And so what you look at to decide whether or not the whole molecule would be polar or nonpolar is you first look at the Vesper notation. So in this case, we have AX4, right? There's no lone pairs on the center carbon. We have 4 bonding elements. If all bonding elements, in this case, fluorine, if all of them are the same, overall, this is going to be a non-polar molecule. So this reminded me of physics, right? For every force, there's an equal opposite force. It's just here you have to kind of think about it 3-dimensionally. So remember, this molecule was set up in such a way to kind of maximize that distance. It's all equal in terms of the bond angles. So what we have is a force pulling up, really strong force, fluorine, but also force pulling down and out. So three-dimensionally, right, overall, the electron density is going to be distributed evenly around this entire molecule. So what you look for is if you have an electron geometry AX2, AX3, AX4, AX5, AX6, you don't want to have any lone pairs because that'll distort everything. And if all bonding elements to the center, right, of all those terminal elements, if they're all the same element, like in this case, fluorine, 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 then overall the molecule will be nonpolar. Now, if I change that just a little bit, and I'm going to use sort of colors here so we can sort of see that. So if I take my tetrahedral shape that we had, and I'm going to mark these green balls, these will be my fluorine. All right, so each of those fluorines, right, pulling equally in its position, right? So overall, we have a nonpolar molecule. But in this one, I've got CHF3. So here's my carbon, hydrogen, and now I've got my fluorines on the base. So now if you replace that top fluorine with a hydrogen, now what happens is you have very strong fluorines, most electronegative element on the periodic table, pulling really hard down into that triangular base, but nothing offsetting that pulling up, right? Hydrogen is about half as electronegative as fluorine. So you've got this strong pull down into the triangular base, but nothing pulling up. So we haven't fit this criteria, right? We still have an AX4 geometry, right? We still have no lone pairs on the center carbon. We still have a tetrahedral shape, but all of those bonding elements in this case are not the same. So you're not going to have the same pull down and out, down and out, down and out, and up like we did with the CF4 to make a completely nonpolar molecule. So this one here, this is going to be polar because we swapped one of the fluorines for a hydrogen. So when we look at polarity, typically what you want to just sort of conceptualize is if a molecule can be nonpolar, right, an even distribution of electrons around the entire molecule, you want to look for an AX something with no E, right, linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, no lone pairs on the center element. And if all bonding elements are the same, it's going to be nonpolar. The exception to that, there's a couple. Of course there are, right? Carbon and hydrogen are almost equal in their electronegativity. One's 2.2, one's 2.1. So if I have methane, the CH4, we'll see this when we do intermolecular forces. CH4 would also be nonpolar. Now, I'm not going to ask you that because I'm going to ask you something that sticks more with the rules, right? Which is we're going to look for all terminal elements, right, to be the same. CH4 would work anyway, though, because anytime you have a carbon-hydrogen bond, though, that is an exception. That one's nonpolar. But we'd still have all bonding elements would be the same. So overall, nonpolar molecule. But the two exceptions to this, if we go back to the chart, and it'll make sense, I think, once we get to the chart. If you have a linear structure, so if I go down here, oops, sorry, go back. If I'm back up here, the two exceptions to the lone pair rule, and I went over this in the video for the worksheet. If you have an AX2E3, you end up with a linear shape. And now the lone pairs on the center element are not affecting the electronegativity pull from the terminal elements. So if both of those terminal elements, which are in a straight line, if those are the same, then you can have a nonpolar structure. The other possibility is the square planar. And I go through an example of that one as well in the notes. I think it was krypton tetrafluoride. But because those are in planes, right, the linear and the square planar, then as long as all the bonding elements are the same, it will be also nonpolar. So it's the exception to the E rule. Normally, if there's any E, that's going to create a polar molecule, but those are the two exceptions, the linear and the square planar. All right, then if I go back to where we were in the notes, the next example we've got, just kind of looking at whether or not it would be polar. We're going to have boron tetrafluoride. We're going to have SO2, and we've got BrCl and we've got N2. And we want to again look at whether or not these are going to be polar or not polar, non-polar. Okay, so let's start with the N2 because I think this one is probably the easiest one. Diatomic nitrogen. We probably remember doing this one. Nitrogen wants to take 3 bonds because it comes in with 5 valence electrons, so it really needs to pick up 3. Both nitrogens are in the same boat, right? They both want 3 electrons to finish out their octet, so they take 3 bonds. It's a triple bond that holds the nitrogen together. It makes complete perfect sense here, I think, that I've got an electronegativity pull from one nitrogen that is exactly the same as the other nitrogen. So overall, we expect an even sharing of the electrons. So there should be no poles here. And that was the simplistic definition we gave in intro, which always works, which is when you look at a bond, if the 2 bonding elements, the nonmetals, are the same nonmetal, then of course it's going to be an even sharing of electrons, nonpolar. And because we only have the 2 nitrogens, this is a linear structure, right? Linear molecule. So there's nothing really to think any further about. With the bromine monochloride, now what we look at is both of those are halogens. They both want 1 electron to finish out their octet. So if I did the complete Lewis structure here with the lone pairs, what I'm looking at with polarity is how that shared pair of electrons, is that being shared evenly or unevenly? And what we expect here is uneven. Chlorine is more electronegative. It's closer to fluorine. So we expect a pretty good pull of the electrons. Bromine is still electronegative. It's just not nearly as much. And so that's going to create a negative end and a positive end, right? An electron rich side, electron poor side. And if you could look at that electron pair, right, with an electron microscope, instead of it being like a nice even oval, like we might see with the N2, it would be sort of lopsided. We would see more of that electron density towards the chlorine and less of it near the bromine. So we have an electron poor side, the positive side, electron rich, right? Electrons are negative, so that's the negative side. But again, not a full +1 -1 because that's an ion. So you give that little curvy D. That's probably not the technical term, but D for dipole. There's your dipole. So this one we would expect would be a polar molecule. Now the boron trifluoride, we looked at this one earlier. We've got boron, 3 fluorines. This is AX3. This is that trigonal planar, right? They're in a plane, not in a pyramid, but trigonal planar. And again, there's no lone pair on the boron. It's an exception to the octet rule, typically only does the 3 bonds. So if we go back to the rule that we talked about, if you have an AXN, whatever that integer is, and there's no E, no lone pair on the center element, if all of those terminal elements are the same, in this case, fluorine, 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 we expect overall for this to be a non-polar molecule. And that's what we would find with boron trifluoride. Now, SO2, we have to be a little bit careful with because we might think that this looks just like CO2, right? Which is AX2 linear. And because it's linear, no lone pair on the carbon, we expect this one to be non-polar because, of course, the 2 terminal elements are both oxygen. With SO2, though, it's a group 6 element. So it actually ends up here with a lone pair. You would have an expanded octet on the sulfur, which you would find out through your formal charges. Because now if you look at your formal charges, all of them would be 0. Sulfur comes in with 6. We've assigned it 6, and that's also true for each oxygen as well. So what we have here is an AX2E, all right? So it's not going to be like the linear shape we saw with CO2, because again, that lone pair of electrons is pushing down on that bonding pair of electrons. So what you end up with here is called a bent molecule. And water kind of looks like this as well. If you're used to seeing the water molecule, you've got the oxygen center, the hydrogens are bent down. It's because there are, or bent up, depending on how you draw it. But anyway, it's because of the lone pairs of electrons on the oxygen. So instead of this being in a straight line, you'd have your sulfur and then your 2 oxygens sort of bent down at an angle. And again, I'm not concerned with memorizing what all those angles are, but this is a bent molecule. So if you imagine the more electronegative oxygens are pulling down and away from the sulfur, but nothing's pulling up to offset that. So if we looked at the molecule as a whole, what we would find is there would be a negative end, right? And then a positive end, right? There'd be a negative side, an electron-rich side down at the base with the oxygens, the way that I drew this. And then that means that we've pulled electrons away from the sulfur, so that's electron poor. So that would be a partial positive. So overall, this we expect would be a polar molecule. But again, the big thing that you look for is either number one, if it's a linear structure, then it's just, okay, are the two nonmetals the same or not? If they're the same, no poles. If they're not, then we expect polar. If we have more like a center element and bonding elements attached, more than just a linear, binary, more than binary compound, then what you look for is if it's an AXN with no E and all bonding elements or terminal elements are the same, we expect nonpolar. If there's an E, that's going to automatically create polarity because you're going to distort somehow how the electrons are going to be shared over the molecule. Because again, like in the SO2, we're pulling down and away from the sulfur, but nothing's pulling up. There's no oxygen up there pulling up to offset that. So it's going to create a negative end and then a positive end on the molecule as a whole. So that would create polar. So an E almost always is going to give you a polar molecule. The exceptions, right, except is when you have your AX2E3, which is linear, and the other one was the AX4E2, which was the square planar. And again, I put those in the video that goes over the worksheet, the chapter 10 and 11 worksheets, so you could see those. But these follow the same thing, that if all the bonding elements, the terminal elements are the same, these can also be nonpolar. All right, but normally if we have an E, that's going to make for a polar molecule. All right, then the next thing we got to talk about is the hybridization of the orbitals. And this is another thing where I think it's easy just to kind of memorize some things. At least that's how I did it. I don't know, maybe not. So what I'm going to do is I'm going to talk about the chart that's posted on page 2 of the notes. And then we're going to attach to that some of the orbital hybridizations. So we have on the chart, we have our total number of groups. We have the Vesper notation. We have the molecular geometry. And then what we're going to do is look at the hybridization, the orbital hybrid. All right, so if you have two groups, right, AX2, three groups could be AX3 or AX2E. Then if we have four groups, we have tetrahedral AX4. You could have AX3E or AX2E2. With five groups, you have AX5, but you could also have AX4E, AX3E2, or AX2E3, and then I'll do the 6 on the next page. All right, so AX2, main electron group, or molecular geometry as well. Those would be the same, linear. AX3 is trigonal planar. AX4 tetrahedral. And then the AX5 is trigonal bipyramidal. All right. So then if we look at sort of the specific molecular geometries, going back and kind of looking at this really quick, I've got my linear, pretty straightforward, center element, two bonding elements, 180 degrees apart. We saw that with carbon dioxide. The trigonal planar, right, that was this shape here. Now what I could do with the trigonal planar is I could have one of these bonding sides be just a lone pair, right? And then what I'd have is AX2 with an E, and you can see that's called bent or angular. I see both, right? The tetrahedral, right, that was this shape here that we looked at. If I replace one of these with a lone pair, right? I still have that same basic tetrahedral shape. Now what this is it's still trigonal, right? Triangle base, but it's not in a plane because of that lone pair of electrons up here. It's in a pyramid shape. So AX3E is called trigonal pyramidal. And then if I take one more of these off, where I have the AX2, but there's also an E2, there are two lone pairs up here. This again, also bent or angular. All right, and then the trigonal bipyramidal. So let me go back up here. We kind of looked at some of these already. The trigonal bipyramidal, the AX5, that's the main group. There's my AX5, right? These are in a straight line. These are in the plane, 120 degrees apart. If I take one of these off, we saw this one with the sulfur tetrafluoride. That's your seesaw shape. All right, so that would be seesaw. And then the AX3E2, that was the T-shaped that we saw with the chlorine trifluoride. And the AX2E3, that was the linear. Now the orbital hybrid, where does that come in? So what we had talked about was when the bonding occurs, the orbitals overlap, and it would be hard to imagine a p orbital overlapping with an s orbital, right? Or a d orbital overlapping with a p orbital, right? How does that happen? So when you look at your main groups, it's really easy. If I need two bonds, I need two orbitals. You always start with the first one being your s and the next one being a p. So I need two, so I'm going to take two, one s, one p. When I need three, AX3, I'm going to take an s and two p's, so s and p2. When it's AX4, right, I need four, so I need an s and three p's. So there's a total of my four orbitals. When I get to AX5, we talked about this. This is going to be an expanded octet, right? So this is going to be sp3, and then we take a d. All right, so what are we talking about here? And just as a note, if it's AX2E bent, it's still going to be sp2, right? When it's AX3E, it's still sp3. When it's AX2E2, it's still sp3. So the orbital hybrid is attached to that electron geometry. So that main group of AXN, right? And again, what makes sense is if I need two bonding sites, I need two orbitals. If I need three bonding sites, I need three orbitals. If I need four bonding sites, four orbitals, five bonding sites, five orbitals. Now, sometimes instead of a bonding site, it's a lone pair, but that still needs an orbital. So that's why it's the same geometry or the same orbital hybrid as what we saw with like the main electron geometry, right? So what's happening here, if I turn the page, is that when I look at carbon, carbon typically ends up with that tetrahedral shape. All right, and so what happens is when I look at an energy diagram, carbon as an element starts out with the s and the p orbitals, right? And when we sort of start with carbon by itself, not bonding yet, so this is just carbon alone as an element, we know it has an S2P2 configuration. But when it goes to bond, right, so now the same energy diagram, it's going to pull the S and P together and create an sp3 hybrid because it wants four bonds, right? Carbon, we know, comes in with four valence electrons, but it really wants four bonds to complete the octet. So what happens is that the s and p orbitals hybridize into that tetrahedral shape. So rather than staying in a spherical orbit or staying on the axes, we learn all about that. It turns out that the orbitals hybridize into that tetrahedral shape. That's actually where that shape comes from. Again, trying to max out the distance between the bonding pairs of electrons. And it creates this sp3 hybrid. And now that those four orbital sites are equal in energy, they're going to spread out. So the two that were paired in the S are going to now take their own seat. And then the two that are in the P also have their own seat. So it still has the four valence electrons that it comes in with. That's still there. It's just what we've done is we've created this hybrid, and it lies in between the energy of the S and P separate. There's your sp3 hybrid, and there's the 4 bonding sites. So just as an example, if we were bonding with 4 hydrogens, like in the case of the methane, CH4, hydrogen each brings in its 1 valence electron, and now we've completed the octet for the carbon. All right, so that's why it's an sp3 hybrid, because it wants 4 bonding sites. So it doesn't really make sense. You can't put 2 bonds in the same p orbital, right? So you have to hybridize those orbitals, spread out the electrons, and then that's why you get an sp3 hybrid. Now, if you look at nitrogen, let's just look at ammonia. All right, ammonia would be trigonal pyramidal. It would still have that same sort of triangular base, that like a tripod base, and that lone pair sitting up top. And when we look at nitrogen by itself, it's an S2P3, right? And what happens here is, yes, those are the 3 bonding sites, but it still does the hybridization. So you have your sp3. It's just one has a lone pair, and then the other 3, right, are the P3 that we had over here. So the S so it doesn't really look a whole lot different. But again, in terms of the shape, it has that tetrahedral shape. So rather than staying a strict spherical S and then the P that are on the axes, they morph right into this tetrahedral shape. And so again, hydrogen would come in and bring 1, 2, 3, 1, 2, 3 valence electrons and complete the octet for the nitrogen. All right, so same sp3. But if I look at the VSEPR geometry, the CH4 was AX4. The ammonia would be AX3E, or the nitrogen trihydride. 4 total groups. I need 4 hybrid orbitals, 1 S, 3 Ps. 4 total groups, 3 plus 1, right? 4 total groups, 4 total orbital hybrids. So that's why when you're under that sort of tetrahedral umbrella, right, where that's the main electron group geometry, the tetrahedral shape, whether it's AX4, AX3E, or even if it was water, AX2E2, where oxygen has 2 lone pairs, right? If I kind of fast forward, it still is going to be an sp3. It's just oxygen's going to have 2 pairs and 2 singles. And the hydrogen would come along and put in the 2 electrons that it brings to the table. So again, we're still looking at sort of the main tetrahedral group. 4 total groups around the center element, 4 total electron groups around the center element, 4 total electron groups around the center element. So they all need 4 hybrid orbitals. So tetrahedral is always going to be an sp3 orbital hybrid. All right. If we look at the notes, because I want to just make sure I'm sticking with the notes somewhat. I know I've kind of gotten a little bit off. So carbon, like we talked about, nitrogen, oxygen, those are all going to keep the sp3. They're under the same tetrahedral electron geometry. When we go to trigonal planar or linear, that's the next part in the notes. The trigonal planar for boron, so boron trifluoride. So for boron, whoops, sorry, that didn't come out very good. So there's my fluorine and my fluorine and my fluorine. Again, looking at it alone, just here's my energy. This is just alone boron. Boron is an S2P1, right? But when I go to bond, I need 3 bonding sites, and I need to bond with these 3 electrons. So I need these 2 to split apart. So there's the 2 from the S, and then I need that 1 from the P. I'm not going to need this 1 orbital over here. So there's my 3 electrons for boron. And so that's why it's only an sp2 hybrid. So this one actually, it's kind of interesting. This one just sort of stays right where it was in terms of energy. It just stays kind of off by itself as an unused orbital space. But what we're looking at is, what do we need to make these bonds come together for this molecule? And anytime that you look at an AX3 main electron group, which is the trigonal planar, Or again, if you had the AX2E, which would be bent, three total groups, you're going to be looking at an sp2 hybrid. All right. Now, with linear, the example we had there was carbon dioxide. And so this one, if you kind of thought about it, you're like, wait a minute, carbon I thought was always sp3. This one's really interesting. So you have carbon starts out S2 and then P2. And what actually happens here is you have a distinction between a sigma and a pi bond. So a sigma bond means that it's a single bond. And then a pi bond is when it becomes a double or a triple bond. And it adds to the sigma bond. So these are pictured in the textbook. I always thought these were really interesting to look at. So if I looked at CO2, for example, I'm just going to try to highlight this. The sigma bond would be in red. So imagine this is your sigma bond. It's your single bond that's holding this together. And then the pi bond, I'll highlight, it adds to what's already there with the sigma. So like this would create a pi bond and a pi bond. So when I look at a double bond consists of one sigma and one pi bond. A triple bond would be a sigma and two pi bonds. And when you look at this the orbital hybrid, what we're looking at here is when we do the hybridization, we look at the sigma. So you would have the sp hybrid. And then what would happen is you would have the pi bonds up at a higher energy level. So what's interesting here is this is going to be the double bond for one of the carbon, like one side of the carbon, and then a double bond for the other side of the carbon. So when you look at your orbital hybrid, you're only looking at the sigma bonds, like the number of like sort of the base. I don't want to say base, but that's the way my brain thinks of it. Like kind of like the initial single bond. Those are your sigma bonds. And I only need two of those. So I need two spots for that. And then the pi bonds are higher in energy. So the double bond, triple bond, that would be higher in energy. So these two together, right? Together, this creates a double bond. And then together, this would create a double bond. And the way that they're pictured in the book I think it's probably a lot better than what I could do. But again, it kind of goes back to the geometry. So if we have an AX2, we need two hybrid orbitals. So it's going to be an S and a P. So in terms of that worksheet or the chart that we had, what you can always sort of tie together is the main electron group and the orbital hybrid. They go hand in hand. So if we have an AX2, we need two sites, SP. AX3, three sites, SP2. AX2E, we still need a total of three sites. It's just one is going to be a lone pair. So it's SP2. AX4, four sites, SP3. Same for AX3E and AX2E2. This was the nitrogen and the oxygen example. We're still just in one of those orbitals putting a lone pair rather than a bonding electron, but we still need the four orbital sites because we still have a total of four electron groups around the center element. Now, when we get to the AX5, we've had to expand the octet. We need five sites. So an S, three Ps plus a D. So there's my five total sites. So we're bringing in a D orbital for the hybridization. And again, that would be the same orbital hybridization if you had seesaw, T-shaped, or linear. And then if we went to octahedral, the last one here, octahedral, which is AX6. So if we have a total of 6 groups, AX6, octahedral, then you're going to have S, 3 Ps, and 2 Ds for a total of 6 sites. And that would be true also if you had AX5E, which is square pyramidal. And then if you had AX4E2, which is that square planar, also SP3D2. So the orbital hybridization is really just tied to the geometry. So as long as you know what the geometry is from the Lewis structure, you know the orbital hybridization. So we're going to look at, in the notes, it asks about that silicon tetrachloride again. We're going to look at the hybridization. And then we already talked about the double and triple bonds, and that'll be it for this Zoom session. But the silicon tetrachloride, we saw this one earlier. This is going to be AX4 tetrahedral. And so you'd have your silicon center, chlorine and chlorine, and then chlorine and chlorine in that sort of triangular base or tripod base. And in terms of the hybridization, silicon is a lot like carbon, right? Same family, so it makes sense. So when you start out just looking at silicon by itself, you'd have your S2 and then your P2. But when it starts to engage in the bonding for the molecule, right, we're going to need 4 bonding sites. So we hybridize and we split up those 2 s electrons and then also those 2 individual p electrons. And so we would take an sp3 hybrid here. And we know that because we've got 4 bonding sites. So it's going to be sp3. But remember when we saw the SF4 and we said, well, why isn't that tetrahedral? For this one, the reason why it was different is we had the 4 fluorines, but we also then had a lone pair. And so now what we're looking at is in our hybrid, we would have AX4E. So we need a total of 5 sites. So if we just jump over to like the bonding hybridization, we'd need 1, 2, 3, 4, 5 sites, right? One would be the lone pair that's on the sulfur, and the other would be the 4 individual sites for the fluorines to attach. So in terms of our hybridization here, we need 5. So we would need an S and 3 Ps and a D. So that would be our orbital hybridization there. So the orbital hybridization really goes back to the number of electron groups, right? And so if you know your electron groups from your Lewis structure, then you automatically know the orbital hybridization. And polarity, hopefully I explained that pretty well. I think playing with the balls and sticks in the lab would really help. But polar molecules, right? That's going to happen when you have an E. So typically when you have a lone electron pair in your Vesper notation, when you have an E, that's going to create a polar molecule. The 2 exceptions there were the AX2E3, which is linear, and the AX4E2, which is the square planar. And the other thing is, or if all terminal elements are not the same, that's when you're going to have a polar molecule. And the example that I had given there was when you had the CHF3, where we were looking at an AX4, right, tetrahedral shape, but we had the 3 fluorines on the base and a hydrogen on top. So if all those terminal elements, 1, 2, 3, 4, if they're not all the same, then that's going to create a polar molecule. So those are sort of the 2 easy ways to decide if a molecule will be polar or non-polar. Typically, if there's a lone pair, right, like on the sulfur up here, if there's a lone pair on the center element, that's going to create an uneven distribution of the electron density. So that'll create polarity for the molecule. The 2 exceptions are the linear AX2E3, makes sense, it's linear, and AX4E2, the square planar, again, makes sense because it's planar. But if all of the terminal elements aren't the same element, then that's another situation where you would have polar. Even though there's no lone pair on the center element, there's no E, all of the X's are not the same element. That'll also create a polar structure or a polar molecule. Okay, so this one, I have to admit, for me was a little bit harder. If this comes easy for you, you're probably going to like organic chemistry a lot more than I did. I'm more of a math person, less 3-dimensional stuff, less spatial drawing, because I'm not very good at that, I don't think. But the more that you kind of play around with it, the better, I think. So in lab this week, we'll get to play with, the kits, which definitely helped me. It didn't make me a better drawer, I'll say that, but it did help me just sort of understand how you can have a pull in all of these different directions, and overall that's going to create a non-polar molecule. And anyway, so that's what we're doing in lab this week. I hope that that helped. And what I did is for the chapter 10 and 11 worksheet, last week we just did the Lewis structures, formal charges, expanded octet, resonance. And now this week I took that same worksheet and added to that the Vesper geometry and then the orbital hybridization. So the video I made on Sunday for chapter 11 was going through that second part of the worksheet, the Vesper notation, the orbital hybridization, and the geometry, the structure of it. So if you want more examples, I think that video would be good if you haven't watched it already. But other than that, chapter 11 just takes a little practice. That's it for this chapter. So I'm going to pause there. But let me know if you have any questions.